The last talk of today's session is Bercel Boldis, who's going to be talking about strong coupling expansion of determinant observables in supersymmetric gauge theories. Please.
Thank you very much. So my name is Bercel Boldis. My presentation will be about based on a recent paper which has been published in the last month. So it is in a collaboration with my supervisor Zoltán Bajnok and Gregory Borchemsky from Paris-Saclay. So thanks for the organizing this whole conference, and also for the cost action to be able to present here. So let's start my presentation. So I would like to give you a brief introduction about ADS-CFT, but most of the things you've heard these on the morning session. So in the scenario what we are considering is the ADS 5 cross S5, which is dual to N equals 4 super Young-Mills theory. The whole idea about the ADS-CFT correspondence is that you can match the string observables with the flat CFT, the observables. Since you can match these observables, you can also match the parameters. What is important for us is that there is the Toft coupling, which corresponds to the Young-Mills coupling, and also the string coupling. And you can make various limits. So, for example, the planar limit, which makes n goes to infinity. This is what we will consider in the next few minutes, and also the strong coupling expansion. So the Toft coupling goes to infinity, or the Young-Mills coupling. This could be familiar, this phase diagram-like diagram for many of you. We are in this regime. So we are considering gauge theory observables, but at the strong coupling. So in the ADS-CFT correspondence, we are going from the classical string part of this diagram. Okay, so what observables, so what are the determinant observables that you've heard in the title of my presentation? So there are several examples for that. So for example, in planar N equals 4 super Young-Mills theory, there is the cusp anomalous dimension, which comes from the renormalization of the Wilson loop with a cusp, or there is the so-called octagon form factor, which is a 4-point correlation function of special half BPS operators. In the dual picture, this is called octagon because in the dual picture it is related to 4 strings scattering, and if you just cut this whole diagram in half, you will get 2 octagons, and you can calculate with that. Okay, but so I was talking about N equals 4 so far, but there are observables as well in N equals 2. For example, the free energy, which has some common thing with the previous observables or quantities. And this is that they can be expressed as a determinant of a semi-infinite matrix. So for those who are more in the mathematical mindset, just can start from this part of the presentation. So this is what we are considering in general, these types of quantities, these determinants. And we are interested in the strong coupling expansion, so the large G expansion of these quantities. So for example, so these matrix, the elements of this matrix, this infinite matrix, are special because it is given by a combination of Bercel functions, as you can see here, and the function, which I will refer to as the symbol of the given observable. This is different for each of the observables. So what you need to define a quantity like this, this function and this additional parameter, actually this small l, which gives the parity of your Bercel functions. Okay, so let's talk about a bit more about this symbol. So this will be important later. So this can be given by by its analytic properties, these symbols. So for example, the small x behavior, which is denoted by this beta parameter. There is also the other parameter which I mentioned, this L. And the only thing that you need to calculate the large coupling expansion is the location of the zeros of this function and the poles of this function. And that's all. And here you can see a table where it contains everything. It's not so important in our case. What is important is that you need only these informations. So, if you consider the large coupling expansion, it was previously shown by Belitsky and Korczemski that how it should look like. So first, you have an expansion in 1 over g. There is a g term, a log g term, a constant, and powers of 1 over g. And they established a method how all of these coefficients can be calculated very effectively. You can see here the first few terms. These are very general expressions in some sense because these only contain these parameters L and beta and some special moments of the original defining function. Okay, but what if we put in all our data from our previous? Yes, of course. It's just a convention actually. So here you can see this is A1 squared. If I remember well, if you go back, so this is a logarithm of some determinant, and if you make it to the exponential, this will be only A1, so it's just a convention actually. Yeah, thank you for the question. Yeah, so this is a list of coefficients, and you can just put in the data that was in the tables for the specific observables, and it turns out if you calculate them numerically, these coefficients will grow factorially. So in the end, you cannot resum them to get a finite quantity. So there should be something beyond the perturbative series, and this is what I denoted with delta fg. This contains exponentially small corrections, as what you can see. Series and at each exponential correction there is also a series of 1 over g corrections. You can see that the exponential corrections goes as the first zero of the defining symbol, which tells us that there is a high, a deep connection between the analytic properties of the symbol and the whole series. Okay, so our aim was to determine this delta f, so the non-perturbative coefficients, and how can we do this? Actually, we can rewrite the whole definition of our observables into a Fredholm determinant. So we have already seen one in Veronica's talk, and it turns out that it will be very useful for us because we can use the tools of functional analysis in the following, and you can introduce some auxiliary functions which will help you determining the whole trend series. First, it seems a bit ad hoc, but at the end, I hope I can give you some sense why it is useful. So this is something like the resolvent of this operator K that is related to the original infinite matrix. And this function, this resolvent, need to satisfy several properties or equations. So there will be 4 what I mentioned, and these 4 will be enough to get all the coefficients in your trend series. So first, you have an integral equation. This one, this seems a bit hard to solve, but you can just pop up a book of integral equations and you will get your solution. This contains oscillating terms and a trend series also in these yet undetermined functions. So the other thing what you can derive from your determinant definition is differential equation. It's actually, if you forget about this last term, this looks like a differential equation for Bercel functions. But here is source term connects this auxiliary function to your original observable. So if you can solve term by term, perturbatively and non-perturbatively for this Q function, the coefficients of this Q function will enter your coefficients of the original observable. And there is also another relation, an integral relation, which basically do the same, just in a different way. So now if we have two different series, we can solve these two equations in parallel, and we have non-trivial connection between the perturbative and non-perturbative coefficients of this observable and our newly introduced Q function. So what I said previously is that Korczemski and Belitsky determined the perturbative terms. They used basically these equations, but you have to get the whole trans-series is the last condition, which we call the quantization conditions. This is just based on the analytic properties of the symbol, what I mentioned previously. So if you consider somehow this combination, you multiply your function with your symbol, 1 minus the symbol, and take the limits where this should disappear. This will give you a relation between different levels of exponential corrections. So, for example, if you put in the first location of your zeros, this will give you the first exponential correction in your Q function. But then you can also solve the differential and integral equation, and it will give you directly the coefficient in your observable.
Can you also get the Stokes constant in this way, or?
No, I think we are working on that actually. So in this paper we don't talk about that, and it's mostly my supervisor's work, but he's determining it by researchers. So yes. But I think you can because by generating this whole data you get all your trans-series. So in the end.
There should be some sort of initial condition. So in Escher myself, I've worked in the customless dimension. Over there, it's an infinite parameter trans-series. So
yeah, sure.
It's very tricky.
Yes,
I think for that, they're very different. So I'm more familiar with the customless dimension and n equal to 2. For the n equal to 2 is a little bit easier. And over there, I think you get basically the purely imaginary Stokes constants.
I see. Yeah.
And the customless dimension, they're not. They're real and imaginary. So I wonder if your sort of functional equation would fix them.
I cannot say about yet anything. But yeah, we hope that there will be another paper which will be more longer, so you can see there every results. So yeah, so okay, thank you. Okay, so what you have seen already is some mathematical tools that you need to determine the whole trans-series, but it turns out that it is very efficient actually, and this is the whole flow chart that you need to put in Mathematica and to determine all the coefficients. So you first solve mathematically the integral equation, and that is enough. That will give you a trans-series. You know the form of the function f that as a trans-series, and you just put it in Mathematica, and it will pop up your coefficients with a very high precision, up to, I don't know, 100 orders. So we have determined the trans-series for our previous cases. You can see here we compared them with the previously known results. And yes, these are basically our results. There are also other terms, exponentially small terms. So, and tuning your parameters, you can get anything basically that you want. So to summarize our results, we considered n equals 4 and n equals 2 and some observable strong coupling expansion. We did a systematic method to determine all the coefficients of the trans series. We verified it numerically at very high precision, and the research and properties were also checked. Mostly my, as I mentioned, my supervisor's work. That's why I haven't talked about that much. Okay, and what can we do in the future? So we can consider further observables related to the Kaspanov's dimension, or this was just one limit of the octagon, so when the cross ratios go to a special limit, we can consider other limits of that as well, or maybe apply our results to other models. So, for example, maybe there are some quantities in QCP or random matrix theory. So that's all I wanted to say. Thank you for your attention.
We have a few minutes for questions. So in terms of the checks of resurgence that you've managed to do, what?
Yes.
So how did you proceed to do that? So, apart from calculating the trans series.
Okay, so we calculated the trans series first. Then with this differential and integral equation, we calculated few hundred terms in the perturbative series. We checked the asymptotic behavior of this, then made a Paddy approximation to get the poles, and then backdoor transform, and compared, for example, the imaginary parts to be killed, and it worked very well.
And have you? Sorry, I have another question. And you were talking about other limits, but have you started thinking about?
No, actually, now we are working on other observables, but I think it's not much harder. You just need to change the symbol in your moments, what I mentioned, and your trans series in the end will be different. I mean, will look more nasty than this, and that will be the only difference. But yeah, we should check that.
Thank you. There's no other questions. Let's thank.